Hello. Okay. Hello, everyone. It's time to begin our meeting. Welcome, everyone. This is the SAVNet working group. This is our second meeting after our working group is established. It's a pity that my co-chair Joe cannot attend the meeting in room. He will participate in the meeting remotely. So here is a note view. I think everyone here know it well, so I will skip it. And here is the working group status. Currently, there are already 9 documents that have been uploaded to the SAVNet repository, which covers the problem segment, use case and requirement, and the SAVNet architecture and solution analysis aspect. For the first part, the draft has been present at the last meeting, and the author of the draft has clarified the concern that raised during the last presentation, and also update their their document accordingly. They will print the update content today. The second part is the SaveNet architecture. This is the first time to presentation in this meeting, and also the some draft that for the some initial analysis for the incentive and the influence for the new solution. And for the in lastly, we will there are also some detailed solutions that aim to solve the similar problem, but may not align with the proposed SaveNet architecture document. We will find some manager to try to sync up them later. And now we are in, according our milestone, we are now in the phase of our first milestone. So the aim of our meeting, we want to adopt the problem segment, use case, and the requirement document during these times. For the submit document, there is one document the bar staff did not put in the 7net report. We expected it later be put into the 7net report for the convenience of the reviewer and the discussion. So here is the goal of our this meeting. Firstly, we will focus on the discuss of the statement problem and requirement and gap analysis draft. And after that, we will discuss the first the initial approach to the solutions, so we can evaluate the gap analysis and the requirement for that we have provide. And lastly, we want to emphasize that currently we our initial goal is to finish the discussion of the problem statement. So after this meeting, if there is no more issue raised, and we will take the adoption call on the mail list. So here is the draft agenda. I have introduced the and the first section is the problem segment. There are 3 parts: intro S, inter S, and the incentive analysis. After that, we will have an open discussion for the document and decided what's the next step that our group will forward. And the second part is architecture part, and we also will introduce the intro S solution architecture, inter S, and the and some of the table table design and principle. After that, we will introduce another solution for the same aim, and the last one is analysis for the current solution. Okay, so I think this is the W chair. So if there is no any issue, I think I want to move forward to the first presentation. Evan.
Hi, Alvaro Rotana, Routing AD. I just want to stress what Asian is saying, which is the charter has 3 parts, right? And we really need to focus on the first one. So, what I would like to suggest to the chairs, of course, is that let's dedicate the time to that. If we start stretching a little bit the time, we need to get those things done sooner. There will be more time to talk about the next steps, architecture and solutions and other things. Well, thank you. So just to confirm what you said.
Okay, thank you. So we'll begin the first presentation. I will. Sorry.
Okay. So, Aijun, can you hear me?
Yeah. Okay. Can you control the slide now?
Yes, I can. Okay.
Okay.
So
then you can begin. Okay.
I will start. So thank Aijun and Jewel for the hard work. Hello, everyone. I'm Danny from Tsinghua University. I'm sorry again that I have to present the draft remotely this time. So next, I will present the updated version of the intra-domain servlet gap analysis, problem statement, and requirements draft. So we know that the goals of this draft is to provide the gap analysis of existing intra-domain solve mechanisms, summarize the fundamental problems of existing intra-domain solve mechanisms, and define the requirements for the new intra-domain solve mechanism. So in the last IETF meeting, we presented the first version of this draft, that is version 0.0. Based on the feedback we got in the last meeting, as well as the comments and discussions in the mailing list. So we made 3 rounds of revisions for this draft. And today, I will present the latest version, that is version 0.3. Let's review the gap analysis we presented last time for version 0.0. We discussed 4 scenarios where existing intra-domain solve mechanisms cannot satisfy the practical requirements. The first scenario is for multi-homed subnet, where asymmetric routing may lead to improper block problem. And the second scenario is that existing intra-domain solve mechanism, that is ingress filtering, only works for the spoofing traffic originated from the subnet. It cannot work for spoofing traffic from inbound direction. The third scenario is the problem for partial deployment. So various reasons can lead to partial deployment for intra-domain solve mechanism. So if some edge routers do not deploy ingress filtering, there is no way for the intra-domain network to validate the spoofing traffic originated from the subnets that directly connect the edge routers. And the fourth scenario is misbehaved router. Last time we presented that a misbehaved router may not faithfully conduct solve mechanism. So since the last IETF meeting, we received a lot of comments and feedback for the draft we presented. We made the summary. There are 4 major comments. The first is that why couldn't you deploy SOF at all routers in the intra-domain network? The second is that defining network elements are trusted or untrusted is very hard. The third problem is that misaligned incentive means the cost of deploying SOF are paid by operator itself, while its benefits are only experienced by other operators. But an intra-domain network is rarely managed by multiple operators. And the fourth comment is that, are we talking about non-IP packets as well? There are also some minor comments. So we just made the revisions for the draft to address all the concerns we received. And the main updates of this latest version compared to the first version, have 4 kinds of major updates. The first is the updates in the gap analysis part. We explain the reasons for partial deployment and remove the scenario of a misbehaved router. So for partial deployment, I think we had lot of discussions in the mailing list, as pointed out by some experts. We acknowledge that there are 2 main reasons for partial deployment of intra-domain SOF mechanism. The first is that the technical limitation of today's intra-domain SOF mechanism may make it hard to deploy SOF on all routers. For example, ACL-based SOF requires manual configuration in dynamic networks. Strict URPF ingress filtering blocks legal traffic in the scenario of asymmetric routing. I think these issues are pointed out by some operators in the mailing list. And the second reason is that some routers cannot support SOF due to router capabilities, versions, and vendors. Actually, the first reason for the partial deployment may be overcome by a new SOF mechanism. But the second issue may still exist for any kind of new intra-domain SOF mechanism. So we still have to take partial deployment into consideration when designing a new intra-domain SOF mechanism. And the behavior gap in the scenario of partial deployment is that when ingress filtering is partially deployed, the spoofing traffic from the undeployed edge routers cannot be blocked by other routers in the intra-domain network. The second major update is in the problem statement part. We remove the problem of misaligned incentive, add the problem of high operational overhead, and revise the description of other problems. Actually, all these points are just the response to the comments in the mailing list. In the latest version, we summarize the problems of existing intra-domain SOF mechanisms. Just 3 major problems. The first problem is inaccurate validation. The behavior gap is that asymmetric routing may lead to improper block scenario in multi-homed connection case. The reason is that existing intra-domain SOF mechanism conducts SOF based on the local FIB, which may not match the real data plane forwarding path from the source. The second problem is limited protection. The behavior gap is that, we may fail to block the spoofing traffic from outside AS or, from the undeployed edge router, because existing intra-domain SOF mechanism only works for traffic from the directly connected sublets. And the third problem is high operational overhead. As pointed out by some operators in the mailing list, the behavior gap is that the manual updates are necessary when there is routing state change in the network, because existing intradomain solve mechanism fails to adapt to dynamic or asymmetric routing scenarios. The third update is in the requirement part. We remove the requirement of direct incentive, add the requirement of acceptable overhead, and revise the description of other requirements. In the latest version, we summarize the requirements for a new intradomain solve mechanism as 3 parts. The first requirement is that the mechanism must ensure accurate solve. The new solve mechanism must match the real data plane forwarding path and avoid improper block under asymmetric routing. The second requirement is that the mechanism must work for all kinds of intradomain spoofing traffic. It must be able to validate the traffic from all directions. Specifically, it should be able to block the spoofing traffic from the outside edge or from the undeployed edge router. And the block should be as close to the source as possible. And the third requirement is that the mechanism must not induce much overhead. It means that we should minimize manual update, avoid data plane packet modification, and limit the number of control plane messages. The final update is that we add 2 new sections in the latest draft. One for the intradomain servlet work scope, and the other for security considerations. First, for the intradomain servlet work scope, we stated that all IP encapsulated scenarios are in scope, including both IPv4 and IPv6 addresses, and non-IP packets are out of scope because our purpose is to validate the source IP addresses, not other source information. For security consideration, we stated that SAVNet focuses on routing protocol-based mechanisms, so the security scope of intradomain SAVNet should be similar to that of intradomain routing protocols. It means that we should ensure integrity and authentication of control plane protocol messages and do not provide protection against the compromised routers that may poison existing control plane protocols. Okay, that's all of my presentation. Comments and feedback are welcome. Thank you. Hi, Ajun.
Yeah, so I know. So if there is no question, I think this topic has been discussed thoroughly in last meeting and also, okay. So there is the queue in the for the question. So okay, wait a moment. Roland, okay.
I cannot hear you, Roland.
Hey, Roland.
You need to press the microphone icon on the meet icon.
Can you hear me now?
Yeah, okay.
Yes.
Okay. I have a question. I see the repeated use of the term intra, I-N-T-R-A. Are we sure that that's actually the correct term to use, or should we be using inter, I-N-T-E-R?
You mean the term? I think, yeah, I presented the intradomain part, and we have the interdomain part later. But I'm wondering which part you mean that we use the INT to represent intra, right?
Yeah, I believe the entire focus, and if I'm mistaken, please feel free to point it out. But I think that we're looking at interdomain rather than intra-domain.
Oh,
Yes, Chair, the charter is explicit that we are looking at both. And that's why we have separate evaluation documents for both, Roland.
I understand, but when I actually read through the documents, it seems like the entire focus almost is on interdomain. Anyway, it's just a linguistic thing. I want to make sure that are accurately representing what we're discussing here for the majority of the documents and proposals. That's all I had. Thanks.
Okay, thank you.
Anthony, okay, your turn.
Hi, Antoine Vuren, Liberty Global. Could you go back a few slides, because I must apologize not having completely read the changes between the drafts. I'm looking for the part of misaligned incentive. There it is. One more further. So do I understand that you removed the part of the misaligned incentive? And I was wondering what the reason was.
Yeah, last time, okay, we made assumption that an interdomain network may be managed by multiple operators. So, okay, there is some deployment incentive problem, but a lot of colleagues in the mailing list argue that usually an interdomain network is managed by only one operator. So the incentive problem primarily exists for interdomain part, not for intradomain part. So I just remove this content. Yeah.
Yeah. So the comment I want to make is that even for interdomain connections, there is an incentive for SAF to be deployed, but it's not so much a technical incentive. It's a very commercial incentive, actually, because when you're implementing SAF, you will see that your traffic on your network will go down for your network and for your customers, which means that you have more capacity on your network. And this is a commercial incentive that people fail to see, because you have to do something for it. You have to convince your customers or your connections, to sign ROAS or to have proper IRR data. But once you start filtering, there is an incentive for your own network. So the misalignment is perhaps not so much technical, but commercial-wise, I think there is an incentive to deploy source headers validation.
Okay, I think you just had a very good question. I think we made a lot of discussions for the incentive problem in the mailing list. Okay, the primary concern is okay, how to encourage an operator to benefit from the SAF mechanism they deploy. I think we will have a lot of discussions in the two presentations later. Okay, I'm
we're
not
techies,
sure.
right? We're techies,
Yeah,
so we don't like, to harass customers and saying, you have to clean up your network administration. It's a dull and boring job. But once you do it, your network will benefit.
Actually, for our two presentations later, we just want to translate this requirement into technical problem. So I hope that we can have more discussions later. But I'm not sure, okay, which part should be put into interdomain part or interdomain part. Maybe that's a problem. We need more discussion later. Yeah.
Okay, thank you.
Jared Mach, Akamai. I just wanted to respond to the last comment here at the mic. If you are running a network and a customer says it works on provider A, but not on provider B, and provider B is the good actor, there is a very strong commercial incentive to relent on that. And what we have to be very cognizant on is that any sort of source address validation may actually break more things than it is preventing, because it is the largest attacks that we see today are not from spoofed packets.
Okay, thank you, Gary.
Hello.
Langdong from Huawei Technology. I also authored this document and just add some additional comments. Actually, we received many comments, valuable feedbacks from the participants, and then list the main 4 comments. Actually, we have responded our comment carefully and sent them in the mailing list, and all the issues have been tracked in the GitHub. So, of course, welcome to join the mailing list, and we can discuss this draft further to improve, continuously improving this document. And about the discussion of incentive, I think there is no question about whether there is no misaligned incentive in the intra-domain networks. The discussion is about the incentive in inter-domain scenarios, right? Yeah. Yes, later our colleges will introduce the inter-domain draft to present how can we improve the incentive of SAV mechanisms by technical uh, improvements. Of course, we can't solve the incentive problem because the commercial factor is the dominant one. Yeah, right. But I believe that we can move one more step to improve the incentive if possible. That will be still very meaningful. Yeah, thanks.
Okay, thank you. We must begin the next slide. If you have any question, I think we can move it to the open discuss after the introduction of the interdomain and the incentive material. Okay. Hey, Lancheng, your turn. I think you can control the slide now.
Yeah, yes, I can.
Okay. So let's begin.
Okay. Hello, everyone. I'm Lan Chengqin from Tsinghua University. We have submitted a new version of source address validation in interdomain networks, interdomain subnet, gap analysis, problem statement, and requirements. Now, I'm going to introduce the updates we have made. This draft aims to provide the gap analysis of existing interdomain solve mechanisms, summarize the fundamental problems of existing interdomain solve mechanisms, and define the requirements for the new interdomain solve mechanism. We introduced the version 00 in last IETF meeting and received several questions and comments in and after that meeting. Based on the discussions in the mailing list, we have been constantly revising the draft in the past few months, and we submitted the version 03 recently. This is a quick review of version 00. We proposed 4 scenarios to describe the gap of existing interdomain solve mechanisms. In scenario 1, reflection attack, and scenario 2, spoofing within the customer coin, existing interdomain solve mechanisms may have improper permit problems. In scenarios of no export and scenario of direct server return, existing interdomain solve mechanisms may have improper block problems. We finally summarized 2 main problems of existing interdomain solve mechanisms. They are limitation in accuracy and misaligned incentive. We have received many questions about the misaligned incentive. For example, some people ask, how is misaligned incentive different from improper permit? Or what incentive does SAVNet hope to achieve? Some people also ask, are we talking about non-IP packets as well? We have discussed these questions in the mailing list, and we make some updates to the latest version. First, we improve the description of misaligned incentive. Misaligned incentive is one of the main reasons why some ASs haven't deployed BCP38. Several publications have also indicated the misaligned incentive problem. BCP38 only prevents the provider who deploys SAF from originating spoofed source traffic, but doesn't protect the provider from receiving spoofed traffic or being the victim of an attack. It means the costs of deploying SAF are paid by the AIS itself, but the benefits are experienced by the rest of the Internet. Compared to BCP38, EFP-UIPF protects deployed AS from receiving spoofed traffic from customer interfaces, so it can provide some direct incentive. However, EFP-UIPF is not well aligned with market demand. It is because that EFP-UIPF only prevents customer code from originating spoofed traffic, but doesn't protect customer code from receiving spoofed traffic from outside customer code. Moreover, an AS doesn't gain additional defense against reflection attacks by deploying EFP-UIPF. For example, in the two cases below, although the victim and its upstream provider deploy SAF, the reflection attack still succeeds. More details will be introduced in the next presentation about SAVNet's incentive consideration for defense against reflection attacks. Finally, we conclude two fundamental problems of existing interdomain solve mechanisms. The first problem is inaccurate solve. Existing interdomain solve mechanisms have improper block or improper permit problems. It is because that they all conduct solve based on local UIP, which may not match the real data plane forwarding path from the source. The second problem is misaligned incentive. Networks still suffer reflection attack even though they have already deployed SAV. It is because that in existing interdomain SAV mechanisms, the victim with SAV deployment does not participate in protecting its source addresses from being forged. According to the updates in problem statement, we further revise the description of requirements. We define 4 requirements for the new interdomain solve mechanism. Requirement number 1, the mechanism must ensure accurate solve by matching the real data plane forwarding path. It should avoid improper block and reduce improper permit as much as possible. Since this requirement cannot be met by using only local RIB information, additional mechanisms are needed to provide the required information. Requirement number 2, the mechanism must provide direct incentive to the AS who deploys SAV. It is required to validate traffic from all directions and help the deployed AS mitigate spoofed source attacks, including reflection attacks. Requirement number 3, the mechanism must support incremental deployment. It must prevent source address spoofing when it is partially deployed in the Internet. Requirement number 4, the mechanism mustn't induce much overhead. It must avoid data plan packet modification and limit the number of control plane protocol messages. We also add 2 new sections. They are interdomain SAVNet work scope and security considerations. For the interdomain SAVNet work scope, all IP encapsulated scenarios are in scope, but non-IP packets are out of scope. For security considerations, SAVNet focuses on routing protocol-based mechanisms, so the security scope of interdomain SAVNet should be similar to that of BGP. If the new interdomain SAV mechanism requires control plane information exchange, there should be security considerations on the avoidance of message alteration or message injection. Thank you.
Yeah. Your turn. Okay.
Hi. What you are saying about the reflection attacks, if this is Sriram from NIST, if the victim of the reflection attack is on your peers customer cone, for example, and you are doing source address validation for your customers, in that case, the reflection attack will be detected and mitigated. So it is not it is not entirely true, the statement you made that EFP URPF cannot mitigate the reflection attack in general. I mean, it's only any reflection attack that is originating in your customer cone and going to your peer's customer cone where the victim is. If you are deploying interdomain SAV using EFP or PF, you can definitely mitigate those reflection attacks.
Well, we can see these 2 slides. If the reflection attack is originated from provider and peer interfaces, it cannot prevent the attack, right?
Yeah, and the scenario I am presenting to you is it's you and a lateral peer of yours. The provider question is somewhat different. If you have a lateral peer and your customer is from your customer cone, a reflection attack is originating, and the victim is in your peer's customer cone, the EFP URPF is able to catch that and mitigate it. That's what I'm saying. So the statement you made is not true across all scenarios.
Yes, shall we talk about the 2 examples in the next presentation? I will show more details to describe how EFP URPF fails to prevent the reflection attacks from provider or from customer.
Okay.
Okay, thank you.
Igor Lubashov, Akamai. So I think it is stating too much that it's always misaligned incentives. There could be cases when incentives are very much aligned. For example, it is a value that if you can detect attacks from your customer cone and, for example, inform them that, hey, you have compromised machines. If your customers are using your IP space, there is value in making sure that your IP space doesn't get on blacklists for originating attacks. There is also value for even directly to your customers. If, for example, if they originate, if they have compromised machines in their networks, now all of their users can start getting captures on all the different websites. And preventing that is also value that is quite aligned. So there is value.
Okay, we want to we acknowledge that EFP UIPF can provide some direct incentive compared to BCP 3.8, but we want to a new interdomain solve mechanism should provide more direct incentive to help mitigate reflection attacks and protect at all directions. Thank you.
Hi, Alvaro Rotana, routing the future-way technologies. If we go to slide 12, this is a individual participant comment. I think in slide 12 is where you start talking about some of the requirements. And if we get to the point where we're going to build solutions based on this, we need to be very specific on what we are requiring. And many of these, I don't know what they would be. For example, just to pick on one, the last one must not induce much overhead. Okay, that's great. I mean, I understand the general purpose of that, but what does that mean? Is much overhead 2 packets, 10 packets, 25, big packets, small packets, what does that mean? So we need to quantify some of these things a little bit better. I know this is the first time that this text is in the drafts, I think. So if the working group decides to keep working on this document and adopts it, we're going to want to look at clarifying these things, right? So that then later we can come back and say, oh, look at this solution. It meets that requirement, right? And so it's easy to, and we're not arguing whether overhead is much or not much, right? Which is not a very technical term. The other thing that I want to sort of throw out there, and this may be a longer discussion for the working group, and something that the chairs should consider in discussing, is the charter specifically says that this working group is not going to extend existing mechanisms, right? It doesn't say that the working group is not going to use existing mechanisms as part of a bigger solution. So, some of the arguments about, yes, this solution, existing solution solves part of the problem, but not all the problem. And depending on where you sit and look at, which is some of the things that Suram was talking about before, we need to consider that. And again, if we get to the point where we're going to go build solutions, what does that mean in the face of existing ones? Without extending them, because that's not in the charter, can they be used, right, for a broader solution or not? Again, just kind of throwing that out there so that it is discussed as we go forward. Thanks.
Thanks.
Roland, okay.
Hi, Roland Dobbins, NetScout Arbor. A couple of quick points on the misaligned incentive discussion. First of all, it needs to be acknowledged that there are, in fact, incentives for some network operators to not deploy source address validation, and those are operators who deliberately and knowingly are actually selling transit to criminal actors who actually have control of the attack generation infrastructure for the reflection amplification initiation traffic, which is what is spoofed, and also for direct path spoofed attacks. And so it's important to understand that there are different categories of incentives, and that there are, in fact, some incentives for some operators to not enforce source address validation on their customers. A second point that I wanted to make sure that everybody understands is that in terms of existing mechanisms, there's been a significant push within the operational community over the last 18 months to encourage more network operators to deploy source address validation using existing mechanisms, whether it's URPF, whether it's ACLs. And we have observed a macro level shift in the DDoS attack landscape as a result of that. We're seeing reflection amplification attacks down across the board. For example, I can tell you that DNS reflection amplification attacks are down 31% from the second half of 2021 and the first half of 2022. And that's true across the board. Also, in terms of the direct path attacks, where you're seeing the attack traffic emitted from the bot or from the attack infrastructure and just going straight to packet the target, we're also seeing spoof direct path attacks down significantly as well. And so it's important to understand that the incentives, the economic incentives, both internally within the perceived economic system of the operator, as well as key externalities, can change over time, and it has changed. And we're seeing even more success with existing mechanisms that are in place today. And I just want to make sure that everybody involved in this discussion is aware of these facts. Thank you.
So okay, we will move to the next next presentation for the incentive consideration. I think this is the most important point.
Okay. Now I'm going to introduce SAVNet's incentive consideration for defense against reflection attacks. This draft further explains the misaligned incentive problem of existing SAV mechanisms and clarifies the direct incentive that SAVNet hopes to achieve. One valuable lesson we learned from BCP 3.8 is the importance of direct incentive for SAV deployment. Although BCP 3.8 has been proposed for more than 20 years, some ASs still do not deploy BCP 3.8 due to the misaligned incentive. Specifically, it only prevents a provider who deploys SAV from originating spoofed traffic, but do not protect the provider from being the victim of an attack. Therefore, to improve the adoption of SAV, the new SAV mechanism must provide direct incentive. If a network deploys SAV but finds that it only helps other networks, the network will not be motivated to deploy SAV. If a network deploys SAV and finds that sometimes it can help itself, compared with not deploying, the network will be more motivated to deploy SAV. Nowadays, source address spoofing can be used in various malicious attacks and is mainly used in reflection attacks. To conduct a reflection attack, An attacker will forge the victim's source IP address in requests sent to the reflector server. After receiving the spoofed request, the reflector server will reply to the victim with a lot of messages. Therefore, preventing reflection attacks depends on the self-filtering on path between the attacker and the reflector. To get protection against reflection attacks, customer or user networks have incentive to ask their upstream providers to deploy SAV to protect their source addresses from being forged. Considering the market demand from customer or user networks, network operators can improve their competitiveness by providing defense against reflection attacks. However, EFP-UIPF is not well aligned with the demand. It is essentially deploying BCP38 at the top of a custom coin. It only validates traffic from customer interfaces, but doesn't validate traffic from provider and peer interfaces. It means that EFP-UIPF only prevents custom coin from originating spoofed traffic, but doesn't protect the custom coin from receiving spoofed traffic or being the victim of a reflection attack from outside custom coin. In addition, EFP-UIPF algorithm B even compromises directionality among customer interfaces. As a result, network still suffers reflection attack even when it and its upstream providers have deployed EFP-UIPF. Here, we first use an example to illustrate why EFP-UIPF fails to prevent reflection attack. We simplify the participants in a reflection attack into three roles. They are attacker AS, reflector AS, and victim AS. In this example, AS1 is the attacker AS, AS2 is the reflector AS, and AS3 is the victim AS. To conduct the reflection attack, the attacker forges the victim's source IP address in the spoofed request sent to reflector. Assume AS2 and AS3 deploy EFP-UIPF. In this case, both EFP-UIPF algorithm A and EFP-UIPF algorithm B fail. It is because that EFP-UIPF only works at customer interfaces, but lacks source address validation at provider and peer interfaces. Therefore, AS2 will permit the spoofed request from provider interfaces, and finally, the attack succeeds. This is another example in which AS1 and AS3 are both customers of AS2. Similarly, AS1 is the attacker AS, AS2 is the reflector AS, and AS3 is the victim AS. The attacker in AS1 will spoof the source IP address of victim to send a spoofed request to the reflector in AS2. Assume AS2 and AS3 deploy EFP-UIPF. In this case, if they apply EFP-UIPF algorithm A, AS2 can successfully block the spoofed request. But if they apply EFP-UIPF algorithm B, they fail to prevent the reflection attack. It is because that EFP-UIPF algorithm B compromises directionality among customer interfaces. It cannot prevent ASs in the same customer coin from spoofing each other. Okay, we have defined several requirements for the new interdomain solve mechanism in the previous presentation. For the sake of description, we temporarily name a possible new solve mechanism as SAVNET. Since there is no specific or mature SAVNET solution yet, we assume SAVNET could meet the following two requirements. First, it could validate traffic from all directions. Second, it could match the real data plane forwarding path originated from each deployed AS. In this way, SAVNet would work better than EFP-UIPF at defending against reflection attacks. In the previous example where EFP-UIPF fails, if in this case AS2 and AS3 deploy SAVNet, SAVNet could notify AS2 of the real incoming interface for source addresses of P1. Therefore, AS2 could learn that packets with source addresses of P1 must come from interface 3. When AS2 receives the spoofed request with source addresses of P1 from AS2 from the provider interface 1, the spoofed request will be blocked and the reflection attack is prevented. In the other example, where EFP-UIPF algorithm B fails, if AS2 and AS3 deploy SAVNet, similarly, AS2 could learn that packets with source addresses of P1 must come from interface 1, it must come from interface 3. Therefore, when AS2 receives the spoofed request with source addresses of P1 from interface 2, the spoofed request would be blocked and the reflection attack would be prevented. Next, I will propose more reflection attack scenarios to measure the incentive that EFP-UIPF or a possible new solve mechanism can provide to the victim network. We still use the simplified reflection attack example, but we enumerate multiple attack scenarios by changing the relative positions of the three roles in a reflection attack. Assume the victim network always deploys solve mechanism because only the victim network benefits from the defense against reflection attacks. Then, for any deploying cases of the other two networks, we check whether the reflection attack can be prevented. If so, the victim can be motivated to deploy solve. If not, the victim cannot benefit from deploying solve. In scenario number 1, where the reflector network is located on path between attacker network and victim network, for all deploying cases, we found SAVNet could work in 75% cases, while EFP-UIPF algorithm A works in 30% cases. EFP-UIPF algorithm B works in 20% cases. In scenario number 2, where the victim networks is located on path between attacker network and reflector network, for all deployment cases, we found SAVNet could work in 100% cases, while EFP-UIPF algorithm A and algorithm B work in 60% cases. In scenario number 3, where the attack network is located on path between victim network and reflector network for all deployment cases, we find none of them could prevent the attack. It is because salve fails when victim's source address shares the same incoming interface with the attacker's source address in the salve rule. In summary, for any attack scenarios or deployment case, we find that SAVNet could work better or not worse than EFP-UIPF. Therefore, a network could have more incentive to deploy SAVNet as the salve mechanism because it would have higher probability of defending against reflection attacks. Thank you.
Hey, Roland, you are okay?
Yes, hi. A couple of comments here. First of all, there is an overemphasis on reflection amplification and an underemphasis on direct path spoofed attacks. And I think that that's something that we need to address throughout all the documentation and discussion here about the problem of spoof traffic in general. Secondly, there is insufficient differentiation between the spoofed attack initiator traffic and the amplified attack traffic. You know, the amplified attack traffic is actually not spoofed on the leg from the reflectors amplifiers to the targets. And I know most of the folks involved in this discussion understand that, but I think that it needs to be clearly documented. Thirdly, I wanted folks to understand that we're increasingly seeing attacks where attackers who can, in fact, launch reflection amplification attacks are deliberately choosing reflectors amplifiers that are topologically sited near the target because the fewer administrative boundaries that the amplified attack traffic has to traverse provides fewer opportunities for detection, classification, traceback, and mitigation. I guess this is almost a question. To my knowledge, EFP or RPF hasn't actually been implemented in any routing hardware, at least in my knowledge. And I personally don't know of any operators who've actually deployed it. And so I'm a little bit puzzled by seeing these statistical comparisons of EFP or RPF, which at least has been specified, but to my knowledge has never been deployed, and then some assertions about SAVNet, which hasn't even been fully defined. So I'm kind of confused by this, and perhaps the previous speaker can help clarify that. That's all I had. Thank you.
Yes, as far as I know, EFP-UIPF has not been implemented in existing routers. Maybe Igor could clarify the deployment for EFP-UIPF. So we are talking about the technical analysis between EFP-UIPF and SAVNet. So there is no mature solution yet, and we just assume a possible salve mechanism could meet the requirements we proposed.
Yeah, I don't think this is actually a technical analysis. I think that this is a theoretical, hypothetical sort of positing of some opinions. It's not really based in fact. Thank you.
Okay, thank you.
So I think after the introduction, there is one open discussion for the as schedule. So I think we can also begin the open discussion, but the period should be cut to 5 minutes. Okay. Hey, Kartik, your turn, okay?
Yeah, you can call me Sriram. Roland, I have a quick comment for you or a request for you before I go to my question. I put a request in the chat box for you to share pointers to the work that you were mentioning earlier about measurements that show that the DDoS attacks have reduced because of deployment of URPF, SAV, etc. I would appreciate that. Again, that
Yes,
was for Roland.
thank you.
Thank you. Can you go to slide 7, please?
7.
Yeah. So one thing to note here is that if AS1 is a provider of AS2, and the attack is assuming that attack is not originating from AS1 itself because it's a provider, it is originating from a customer of AS1. And if you deploy the SAF technique, EFP or PF or whichever one is best on the customer side of AS1, that is where that attack is most successfully prevented, because you cannot move up the chain of customer to provider and try to implement these techniques very effectively at the higher levels in the hierarchy. So what you have to do is you look back down towards the customer cone again, from AS1 down to into its customer cone. And if the SAV mechanisms are implemented there, then the attack is prevented in the even like it's not successfully emerging out of AS1 to proceed towards AS2. So that's something that to keep in mind. And as you move higher in the hierarchy, in the customer provider chain, what happens is that it becomes, it becomes less effective. You have to, unless you do a lot of things, lot of additional overhead, unless you do that, what happens is that at the higher levels in the hierarchy, it is harder to implement, it is harder to achieve the objective of directionality that you have been talking about. You would have to sort of resort to a feasible, a loose URPF, for example. It becomes harder to implement, achieve good sense of directionality at that level because basically because the complexity is higher, the customer cone is much larger, and there are difficulties with the implementation, of course, at that level. But at the lower levels, if you implement it on both sides, not only on the customer side of AS2, AS3, but also on the other side of AS1, where the traffic is, then these things work much better. So that's one comment. If you have, I can pause.
Yes, to achieve accurate SAV at provider interface is much more difficult than achieving accurate SAV at customer interface. Yes, but IFC 8704 recommends to deploy loose UIPF at provider and peer interfaces and deploy EFP UIPF algorithm B at customer interfaces. But to simplify the manual configuration overhead for deploying SAV, we need one mechanism that can validate traffic from all directions, instead of applying different SAV at different directions, right? Besides, we should pay more attention to SAV at provider or peer interfaces. Yes, it's a difficult task, but it is a really necessary requirement, and it is meaningful, is worth doing.
Yeah, and my other question is, like Roland pointed out, what you are describing here is SAVNet. You haven't described what SAVNet is. Perhaps you are referring to the another one. I think that is the architecture document. So at this point, I think it is still like a continuation of the requirements, how EFP, URPF, or other URPF don't meet the requirements, and how the new requirements for SAVNet will overcome the limitations of the previous methods. So I think that's what you are doing here, but you don't really have a solution that you can call SAVNet at this point, uh, unless you are referring to the another document that is the architecture document. So I would be careful to say that there is this solution and it performs better than EFP URPF.
Yeah, now, okay.
Hello, Nangon from Huawei Technology. Uh, just to clarify this document, something about this document. This is supporting draft and it's temporary. So it should, incentive is a hot topic and have many discussions in the mailing list. So we have decided to make individual draft. Actually, it should be included in the interdomain problem statement draft. This draft is actually a technical analysis result, presents some technical analysis results. We do not give some implementations, and something may be misleading in the presentation. SAVNet is not a solution, maybe two more solution like information is provided in the presentation. Actually, there is no more to SAVNet that can perform, can meet our requirement in the previous problem statement draft. Okay, that's all.
So let's begin the second part of for the SAVNet architecture. So before we introduce the intra or interdomain architecture, first the author will like to introduce the Savvy table architecture for the discussion of the next two slides. Okay. So I can change the slide as required. Okay.
Okay. Hello. Yeah. Hello, everyone. Glad to give a presentation here. This draft is not a solution draft. We will describe abstracted source address validation and some typical validation modes so that we can easily to understand which kind of SOA table can be generated or used in different scenarios. Next slide, please. So why there is such a document? SOA tables are used for filtering specific source prefixes, and they can be generated manually or automatically. In the data plane, they are implemented by SL, FIB, or some other resources. It's important for engineers and operators to understand which kind of SOA tables should be used in particular scenarios. But the existing SOA mechanisms have their own data structures. These data structures are coupled with corresponding underlying implementations. And there is no unified data structure for the SOA table. In different scenarios, the levels of validation accuracy and validation strictness are different. So it's not easy for us to understand which kind of SOA table can be generated or implement or enabled in the data plane. And finally, for validated packets, we may take either permit action or block action, but sometimes those actions are not feasible enough for us, so we're just using multiple available actions for meeting diversified operation requirements. Next slide, please. About this draft, we give abstracted SOA table, and any existing SOA tables can be expressed by this abstraction. Based on the abstraction, we describe the four typical validation modes, and as well as their application conditions. Finally, we start using multiple actions for different operation requirements. This draft can help engineers to make the design goals clear, to help them design new SOA mechanisms to improve the existing designs. And they can also provide guidance to operators to tell them which kind of SOA tables can be chosen in particular networks. Next slide, please. This is SOA table abstraction. Is very simple. For any kind of SOA tables, we will check whether a source prefix arrives from a valid interface. So there are two dimensions in the SOA table. They are source prefix and the interface respectively. Any existing SOA table generating mechanisms is to fill this table. In the table, each cell indicates the validity state of a pair of source prefix and the interface. The state can be valid, invalid, or unknown. The more complete the table is, the more strict the validation is. And the more accurate the table is, the less improper block and improper permit there will be. And there is only one SOA table abstraction in this document on one device. Next slide, please. We can configure SQL rules to do ingress filtering at different interfaces, and we can easily express this kind of SOA table by using the described SOA table abstraction. And another example of strict URPF can be found in the backup slides. Next, please. Okay, what can we do by using the abstract SOA table? We define some typical validation modes that describes the typical validation procedures. Why do we need these modes? Why do we define these modes? In different application scenarios, the SOA tables may have different levels of accuracy and validation strictness. So we define some validation modes that are suitable to different scenarios. And these modes can help us to easily understand which kind of SOA table can be generated and enabled in the data plane. There are four validation modes. Mode 1 is interface-based prefix allow list. We are very familiar with this mode. Most of the existing SOA tables are trying to generating accurate SOA table under mode 1. This mode is used for strict ingress filtering. If we want to use mode 1, we need to learn the complete set of source prefix that may arrive at the configured interface. And mode 2 is interface-based prefix block list. If we are sure some prefixes are not invalid for this interface, we can put them into the block list. Besides mode 1 and mode 2, we have mode 3 and mode 4. They are prefix-based interface allow list and prefix-based block list. Actually, they are similar, so let's talk about mode 3 only. Mode 3 is less considered in the existing SOA mechanisms. If we want to protect the specific source prefix, we can use mode 3 or mode 4. And if we cannot obtain the complete set of source prefix, we can also use this mode. So by choosing different modes in the suitable application scenarios, we can provide as much protection as possible. Next, please. The procedure is simple. We will look up a SOA table. in specific mode by using a social address and the incoming interface, and we get validated state. Next. Thanks. No, up. Yeah, thanks. There are many available actions that can be picked for the validated package. There are permission, block, rate limiting, or sampling. Even for even for the package with invalid state, we can use permit, block, rate limiting, and sampling actions to do. We can use sampling actions to do further analysis. For example, yes, they are for meeting diversified operation requirements. Okay, that's all. Thanks. One more word. This draft doesn't focus on how to generate and implement the SVA table. Yeah, it's a supporting draft.
Okay, Jared.
Jared Mach, Akamai. So if you go back, I think it was one slide where you were talking about, the potential to, sample the packets, or even rate limit them or something. No, forward. But this is something that many of the operators are already doing. Is they're actually, they're already collecting data through either NetFlow, IPFix, or SFlow based collectors to go and trace back when there are spoofed packets on their network. But I'm also struggling a little bit in a multi-tenant environment. So if I have an L3 VPN type of environment, I may not know all of the source IP addresses that are valid in that entire environment. So are you talking here about having all the routing protocols and all the AFI-SAFIs and VPNs contribute to the SAV table?
Thanks, Jared. Yeah, it's an interesting question. The answer is no. We don't assume that all the routing protocols will work for SAVNet. Yeah, we just said that we can take a sampling action into consideration because it will help us to analyze where the text come from, so that we can do better ingress filtering. Yeah.
But one of the things you need to do is to make sure that if I have IBGP, for example, I need to make sure that that contributing, /128 or /32 route gets into the SAV table so I don't drop the source packet of the BGP session in my IGP. So you do need to go and create a contributing table out of all of the routing protocols involved. And if we're going to try and describe how to, here where you're talking about some of the prefixes are known, all of the prefixes are known, and some are known and some are unknown, we need to have a way to take all of those connected interfaces that may be assigned from a provider, an internet exchange point, for peering or something like that, that is a valid source address for a packet, especially like an exception packet like a ICMP error or TTL expire or something like that. We need to ensure that all of those are still flow through these networks and are not dropped, because that is important operational information that's needed to debug the networks when there is a problem. So we do need to make sure that there is some way to contribute from those other routing protocols to build really what we're talking about is a superset list from multiple data sources.
Yeah, thanks. Yeah, we just provide some options for the validation modes. We must justify which mode can be used in the target networks. So we give some application suggestions in the draft. Yeah, thanks.
Okay, thanks. We'll move to the. Yeah, we have no time for discussion. We must move to the next presentation. Okay. Yeah.
Okay.
Yeah.
Morning.
Okay. Mm.
Can you hear me? Okay.
Yeah. I think you little closer to the mic.
Oh, okay. My control the slide.
Yeah, you can control.
Oh, okay.
Offline. 哎，now now can you introduce the? Oh, okay. He returned to the meeting. Okay. Okay, fine. Can you control the slide now? Hello, Fan. We can't hear you.
Can you hear me now?
Yeah. Okay.
Okay. Morning.
Let's begin.
Sorry.
Yeah. Let's begin.
Could you help me control the slide? Jun, could you help me to control the slide?
I have give a control to you. Okay.
But
You
it
can
don't
control
work.
the slide.
It don't work for me, I think. Okay, I will try. Okay. Let's start now. This is Fang Gao from Zhongguancun Laboratory in Beijing. The topic of my presentation today is about architecture of intradomain sublight. I will introduce this in the following three aspects: goals and requirement analyzing, sublight per flow, and the effect of sublight implementation. At the first beginning, let's have a review about the gaps or problems of existing intradomain submechanism. For the URPF, it has the limitation on scenario, which is projected as the improper block and the asymmetric routing scenario. And it also has the limitation on the directions. It cannot cover the spoofing traffic come from outside the AS and come from the incapable or undeployed edge routers. On the other hand, ACL-based English filtering seems workable in most scenarios on technical, but it needs continuous and complex menu configuration to keep the accuracy. So if subnet want to resolve all these issues, the following functions need to be considered or provided. For the perspective of accuracy, subnet need to obtain completely source prefix in the multi-homing scenario and identify accurate interfaces in the asymmetric routing scenario, just like the PPR or even the different bidirectional IP coast design. I think all of those are some popular and ordinary deployment in most of commercial networks. And for the aspect of direction, subnet need to try to support validated traffic from all the directions. If it could work at more routers, it will have the chance to protect the spoofing traffic as close to the source as possible, and could have the chance to block the spoofing traffic from outside the AS. On the other hand, providing an approach to generate sub-rules dynamically is also an important goal and requirement, as it could help to make the maintenance cost to be affordable and correct sub-rules according to changes in the real time. So, in order to meet all those goals, the key idea of sublight is to trying to generate an independent and accurate subtable on each router, which follows the real data plane. Exactly, it's discovering the real data plane forwarding path via hop-by-hop notification, and then generate sub-rules hop-by-hop along the path. After the sub-rules generated on the data plane, we have a diagram figures showing how it processes when a packet comes in. Before it look up the fib table by the destination IP address, the source address will be validated in the subtable via the subrules. And through this new procedure, it can support validate packet received from all directions and protect the source prefix of the deployed error from being forged. Okay, I will show you the overall architecture through the diagram on the right side. There are two components on the control plane, SPA and SPD. Both of them are targeted to generate subrules on the data plane, and each one have a corresponding protocol message. The first component on control plane is the SPA, source prefix advertisement. It has three tasks. At first, it needs to obtain complete local source prefix. Then it will support to generate subrules on the ingress interface of each edge routers. Then support SPD to generate subrules by providing the source prefix via SPA messages. We mentioned the SPD just now. SPD is the second component on the control plane. We call it as source path discovery. It will identify the accurate incoming interface for source prefixes by discovering the real data plane forwarding path. Then generate subrules on network-to-network interface of each intermediate routers. Short summary here, through this new mechanism, SAVNet will try to apply in more scenario of the real network and on all directions, whatever is the inbound or outbound traffic, and with an automatic manner for generated subrules. Okay, in the following slide, I will expand on the core flow of the SAVNet and show how it works in each step by some examples. The first step is SPA. We record the target of the SPA is to obtain the complete resource prefix. Let's take a look at the figure on the right. Each router in the domain will conduct as an orange router and allows its source prefix to all other routers in the domain by the SPA message. And the SPA receiving router will generate a table to store the relationship between the orange router ID and the source prefix belongs to it. It's just as shown in the bottom left. If something sounds not so complex, I want to highlight here is in the multi-homing scenario. We take a look at the route 1 and route 2, for example. A tag mechanism will be adopted here for the source prefix synchronization between these two routers. A tag value is an identifier of the same consumer, and it is taken in the SPA message. It will identify the source prefix and the interface belongs to the same consumer, and help to get the complete source prefix for the two routers and the interface pair. Next, after SPA procedure, let's take a look at what will happen in the subtable of the edge routers about the subrules generation of the ingress interface. We still take the subtable of route 1 and route 2, for example. And it's also on the bottom left. The record in the black color is the source prefix come from the local information. So it's the similar things with the current sub-mechanism. But the record with green color is the source prefix achieved by SPA synchronization. And just this new green record will dedicate to avoid improper block in the dual homing scenario. And that is definitely one of the reasons why adopt a mechanism of cooperation between routers on the control plane. Okay, then let's go to the last step. It's source path discovery, SPD procedure. SPD procedure is task to generate subrules on the intermediate routers and the network-to-network interfaces. The main idea of SPD is like that. Each router sends the SPD message on the preferred path according to the real data plane information. Then the receiving router knows the incoming interface and binding this with the source prefix and generate sub-rules on the data plane. Actually, SPD is an operator group which consists with 3 substeps. We look at the figure on the right. This time we take the root 3 for example. Root 3 will generate an orange SPD message for the prefix of P1 and P2 on the left. To the next hop, root 6. On root 6, after it receiving the SPD message from root 3, it will generate sub-rules according to the incoming interface at first, then execute the renaming operation to the received SPD message. Then it will go to the next hop of root 5. On root 5, the operation is similar with the root 6, so we will not repeat here. And go ahead. At last, the SPD message reached the last node of the destination, P1 and P2. The root 1 and root 2 will generate sub-rules at first, according to the incoming interface. Then execute the termination to the received SPD messages. Until now, the whole SPD procedure is done, and the sub-rules generated on each hop of the whole SPD path. I want to highlight here is that in order to guarantee the accuracy of the incoming interface during the full SPD procedure, all factors that influence the forwarding path, just like the fiber forwarding or PBR, will determine the directions and outgoing interface of the SPD message on each hop. Okay, that's all of the co-op flow, and we have a quick summary again. It is the benefit achieved by subnet and comparing with the existing staff mechanism. We look at the diagram again. By this new mechanism, subnet can apply to more scenarios, just like to the 1.1 multi-homing and 1.2 asymmetric routing. And the subnet can protect deployed area from spoofing attack on all directions, just like the 2.1 for the spoofing traffic come from outside the AS, and 2.2 for the spoofing traffic come from the uncapable or undeployed edge routers. And the third is that the subnet can generate sub-rules dynamically, which will reduce the maintenance cost. Okay. For today, we are focused on the co-op flow, considering most of the people were interested with the convergence and the partial deployment things. So I simply need some design principle of them here. For the convergence, the principle is balancing performance and overhead. So it will be fast new sub-rules installing and slow sub-rules removing. The basic mechanism for convergence is a mixture of periodic updating and agent time expiration. If we want to faster the convergence, a triggered updating mechanism or backup sub-rules preparation in the FRR scenario is also could be adopted. And for incremental deployment, the principle need to consider about the device capability and the IGP error design. It is recommended to deploy from the higher ability device and aggregation of core layer and the backbone area of the IGP, and then expand to the lower capability device, access layer and no backbone area of the IGP, gradually step by step. It's just some simple principle here. We can have further discussing offline and mailing list. Okay, this is the final summary. We mentioned the goals of interdomain subnet and the architecture of interdomain subnet, which is consisted by SPA and SPD procedure on the control plane and a subtable in the data plane. At last, the architecture is protocol independent. Extension of the routing protocol are not focused and mentions in today's document. Okay, that's all about the topic. Thank you for listening and welcome to your comments.
Okay, Ronan. I think because the time is critical, so we must make a comment. every conveniently. Okay.
Yeah, very quickly, I just wanted to point out that in the intra-domain case, it's important to understand, and in the inter-domain case for that matter, that the majority of spoofed attack traffic, whether it's direct path DDoS attack, or whether it's the spoofed attack initiation traffic that's used to stimulate reflection amplification attacks, the majority of this traffic is actually generated by server class machines in data centers, internet data centers, IDCs. And there's a well-known mechanism, it was actually described in an informational RFC, which I put in the chat, that's called Draft Baker Sava Cisco IP Source Guard 00. It's called IP Source Guard, and it's a mechanism that actually operates at the switch level. And I'm kind of, it's surprising that I haven't seen any discussion of that in this working group, especially in the intra-domain use case. And then secondly, when we come to cable types, CMTS types of access systems, there's another mechanism called Cable Source Verify, which is very similar. There is no draft that actually describes this to my knowledge, but it's not patented technology. And so I think that we need to take a look at this, especially since it's this is a mechanism that is an intra-domain deployed mechanism that can work quite well. I just wanted to make sure everybody in the working group was aware of these two mechanisms. That's all oh, and finally, there's a typo. The convergence ends with an E, not with a Y, just a minor thing. Thanks very much. That's all I had.
Okay, thank you.
Hi, Alvaro Rotana, Futureware Technologies, comment as an individual participant. So when I look at this architecture, clearly that table that we're trying to build seems to be the focus of the architecture. However, this document defines or is based on the assumption of a specific solution, right? There are many mentions in the presentation around periodic updates, and even a discussion at the end around incremental deployment and how do we converge faster and things like that, which are related to a solution, right? Not related to what the architecture might look like. The point here is that the architecture can still be met with different solutions. And what I would like to see is this document to be a general document of what we would like to, again, the high-level architecture to be, not the solution. The solution is going to come later, and it is something that we will need to discuss, of course. So I think that, again, this document can definitely be generalized without losing the advantages that are trying to be presented here. Thanks.
Yeah.
Okay. Hello, everyone. Yangon from Huawei Technology. Next slide, please. In this presentation, we will share some preliminary ideas that is to narrow the gaps of existing interdomain SOA mechanisms. Here lists the three main gaps. They have been described in the problem statement draft. First is improper permit, and the second is improper block, and the third one is misaligned incentive. Next slide, please. So how to narrow the gaps? We think about. Oh, okay. So how to narrow the gaps? We think about generating accurate SOA rules at all directions of the validation AS. The validation AS is a AS can conduct source address validation. There are two key points. First is accurate SOA rules. That means accurate source prefix and accurate incoming interface. And second is at all directions. Generate rules at every interface of an AS. There are two expected results. Result one is if we have accurate, more accurate SOA rules, we can reduce improper permit as a provider interface, and the incentive can be improved, can also be improved a little. And the second result is if we have accurate SOA rules as a customer interface, we can avoid the improper block and improper permit in some particular scenarios. Next, please. To achieve this goal is not easy. We need to overcome some challenges. For validation S, if the validation S want to generate SV rules for the source prefixes of an orange AS, there are usually 3 steps. Step 1 is to get the source prefixes of the orange AS. Step 2 is to obtain the real incoming direction of the packets coming from the orange AS. And step 3 is to generate SV rules by binding the source prefixes to the incoming interface. The challenge 1 comes from step 1. How can we get the accurate and complete set of source prefixes of the orange AS? And the challenge 2 is how to get accurate and complete incoming directions of the orange AS. By using the local RIB information is not enough, so the main idea is to allow ASs to cooperate with each other. They can exchange some extra information. To address challenge 1, we use source prefix advertisement process, that is SPA process. The main idea is simple. The orange AS can announce the hidden prefixes to the validation AS. Even the prefixes are not announced by BGP, the validation AS can learn the prefixes owned by the origin AS through the SPA message. This process can be used in the DSR scenario. Next, please. And the second is SPD process. Orange AS can advertise its preferred AS passes to the validation AS. Then the AS passes connect the Orange AS and the validation AS. Then the validation AS will learn the real incoming direction, and any other directions will be considered as invalid. Even their relationship between the neighbors and the validation AS is C2P, P2C, or P2P. Next, please. Yeah, here are some potential improvements. Improve 1, we can deal with improper block problems in the DSR scenario. And second is eliminate improper block in the no export scenario. Next. And improve 3 is about the incentive. We can have a relatively more strict validation as a provider interface, and the reflective attacks can be blocked here. So the source prefix can be protected by the validation AS. And finally is no improper permit. Yeah, okay. Of course, to achieve this goal by using SPA and SPD is not enough. If the AS paths in the control plane and the data plane are not inconsistent, the results may be not good. I mean, there may exist improper block problems. So we have some preliminary ideas that the AS can advertise the redirection as passes to the orange AS, so that the validation AS can also learn the redirection path from the orange AS. Next, please. Here are some considerations. We have some analysis in the draft. Next, please. Yeah, really a quick presentation because due to time limitation, this architecture is protocol independent. Welcome to leave your comments or questions in the chat box and the mailing list. We will respond to them one by one. Thanks.
So we will leave no time for discussion, and we'll move to the next presentation. Yeah, Lauren, would you like to? Oh, so I think we have 1 minute for a question. Roland, okay. Roland, it's your turn for the question. Oh, okay. Let's begin.
And on my part, please proceed.
You'll drive the slides? Yeah. Okay, thank you. Hey everybody, I'm Igor. Last time at last IETF, we talked a little bit about BarSav, one of our solutions. This is a work we're doing with Cider apps, but it's super relevant, so we wanted to make sure we keep you appraised of what we're doing. Next. Thank you. So this is just a list of requirements for SAV as we're looking at them. Again, we're not boiling the ocean. We're just protecting a network, looking at only the customers and peers. We are not protecting from traffic from coming from provider, just so to be sure. But anyway, the requirements for SAV we're seeing is obvious. The most important thing by far is improper block. That's basically, if you have improper block, that's what gets you not implemented, because that's a network optimized for the most. Don't break their customers. And obviously, improper permit or otherwise, what's the point? So just can't emphasize it more. The rate of improper block, you should really be competing against lose RPF. So that's the goal. And comes hand in hand, high quality implementation is required. No matter if your algorithm is vague or too complicated, and it's not implemented right, like it's almost as good as you don't have a good algorithm. Next is incremental deployability. Super important. Business economic incentives is a key. If you're the first adopter and you don't get benefits, you don't implement it, and therefore we don't have adoption. Especially there should be benefits for early adopters. So there are some benefits to protecting just traffic going up from your customers or from your peers. I mean, your reputation of your OS is important. Stopping your traffic, telling your customers that they have a problem it could be useful service. And like it was said before, if you're spending a lot of bits, a lot of capacity and garbage, well, that's your network capacity too. And depending on your cost structure, it may be actually a good idea not to pay for transit for traffic that's garbage. All right, and ease of adoption. It's usually an overlooked factor, but it's very important. Human factors are huge, so it's a very important thing. And network effects, that's kind of later. If everybody is adopting SAV, maybe some government will require it. But so anyway, next. I'm not going to. No, next slide, please. Thank you. I'm not going to describe it in detail. Basically, the ParSav is just taking BGP data that's usually that other algorithms are using and augmenting this RPKI data for cases where there is asymmetric routing or any other sort of traffic engineering. We can get information about prefixes as well as customer relationships from RPKI. There is a detailed presentation, so I'm not going to go into much more detail here. Next. Again, this is a general operation of it. You can read the slides. Basically, compute the customer cone by following ASPath relationship in BGP as well as ASPA when available. Once you have the customer cone, which is a set of AS numbers that are your customer for any particular interface. You compute it separately for each interface. You look at, again, BGP matching originating AS and prefix, as well as raw data that's registered, and compute the set of CIDR blocks. And that's your AS filter for the SAV. Next. And this is basically my last slide, how we are measuring against what we're doing for our requirements. We are trying to reduce first and foremost improper block by discovering more prefixes and more AS numbers using information not available in BGP. We have in the new draft implementation guidelines for trying to improve the quality of implementations. It doesn't require signal from anybody else, so it's deployable, and it doesn't require people to learn any new technologies beyond BGP and RPKI. So it's like easier for people to understand. Right. It doesn't require new hardware, really, as long as you have a little bit of memory for the new sublist. You can use VRF on existing hardware. You just need to make sure you can load it. And that's about it.
Thank you, Igor. So I think this is one kind of SAV table at one kind of measure to format establish the SAV table. Okay.
Thank you.
Yeah, Roland, okay.
To make a general comment that this direction seems to be, to me, to be more in alignment with the actual statement in the working group charter about making use of existing mechanisms and not extending mechanisms, but rather we're actually looking at potentially weaving them together. And so of all of the potential approaches that have been discussed so far, this general approach to me seems to be the one that at least a vector that has a higher potential degree of success than some of the others.
Hey, Menxiao, I think you can begin the presentation now. Thank you.
Oh, okay. Can you hear me? Chair, can you hear me?
Yeah, okay.
Okay, thank you. I'll be quick. Hello, everyone. This is Meng Xiao from New H3C Technologies. This presentation is about analysis of sub-data plane performance based on an implementation of independent step table. We've heard some concerns about the data plane performance since last meeting, whether of the existing set mechanisms or new ones. One of the main purposes of this draft is to address those concerns. I think Nan has already given a good presentation about the basic idea of step table, so let me just skip this slide. In order to improve the accuracy, new SAVNet mechanisms are expected to generate step rules based on the real forwarding path. So independent step table may be required. Actually, the existing EFP URPF already requires independent step table, or referred to as the RPF list, but EFP URPF has never been coded. In the draft, we describe a possible method to realize independent step table on data plane. As shown in the figures, each line card has a local table which stores part of step rules that are related with its own interfaces. The keys of local table are source prefix and valid incoming interface. No result zone is required. A global table is also used to store all the known source prefixes, which is a union of source prefixes in all local tables. And the figure shows the packet processing procedure. You can read the draft for more details. I'll just skip it here. Yeah, this slide shows the performance testing including some existing mechanisms and the independent subtable. The tested equipment is an H3C CR device. The test traffics are IPv6 small packet flows at line rate. Performance is evaluated by PPS. Compared with plain forwarding, the performance loss of different SAV mechanisms are all around 5%. The performance of independent SAV table is roughly equivalent to URPF. We also tested the independent SAV table mechanism under different scales of source prefixes, and the performance has no substantial changes. The next step is to revise the draft according to feedbacks, and any questions or comments are welcome. Thank you. Yeah, that's all. Thank you.
Darren, do you have any question?
Yeah, I was curious. Based on the requirements, there's only a few requirements that I saw in the analysis drafts, and I was wondering how, like, we've seen this SPD table stuff, and I'm just new to this, so excuse my unfamiliarity with it. But I've seen the SPD table stuff as kind of one solution, maybe not an architecture, but it looks like a specific solution. And then the bar SAV stuff is there any analysis that the group has done on, you know, comparing these two things, like existing technology solution versus the SPD table? This isn't specifically for this presenter, but if you know something, that would be great. Thanks.
I think this data plane SAV table can be used by different control plane mechanisms, and is not limited to a specific solution.
All right, thanks.
Thank you.
Hey, Roland, okay.
Very quick question. Is the source code and the implementation details for the SAV mechanisms that were listed in the performance table, is that information publicly available?
Sorry, the source code is currently not available, and we just implemented an early prototype. I'm sorry.
Very helpful if folks could be allowed to examine the source code. Thank you.
Okay, thank you for all coming. So we must close the meeting, and for the further discussion, I think we can put it in the main list. Thank you for, okay.